So WPA encryption, Wi-Fi protected access encryption. Wi-Fi protected access is a security protocol defined by 802.11 IE standard. WEP uses 40-bit or 104-bit encryption key, whereas TKIP uses 128-bit key for each packet. For each packet is the key here. TKIP uses Michael integrity check algorithm with a mic key to generate the mic value. So TKIP, under TKIP, the client starts with the 128-bit temporal key TK, that is then combined with the MAC address and with an IV to create a key stream. Note that in WEP, key stream was generated using RC4 on WEP seed, which contained WEP key plus IV. So this key stream will be encrypted using RC4. It implements a sequence counter to protect against replay attack. TKs are changed every 10,000 packet, thus protecting from key reuse. So all newly developed Wi-Fi equipment uses either TKIP or AES encryption. AES is under WPA2. TKIP is under WPA. So WPA is based on pre-shared key authentication and 802.1x EAP, extensible authentication protocol for enterprise mode. So PSK is for personal mode and EAP 802.1x EAP is for enterprise mode. PSK is shared between AP and client, same as in WEP. Temporal Key Integrity Protocol TKIP is used for encryption. For message integrity, MIC message integrity check is used. With MIC, WPA uses an algorithm named Michael to produce an authenticated code for each message, which is termed the message integrity code. The message integrity code also contains a frame counter or sequence counter to provide protection over replay attacks. Unlike WEP, instead of using the same key for each packet, the keys are generated dynamically. With simple firmware updates, we can move from WEP to WPA. TKeep was considered as temporary patch for WEP. Here key is temporal, hence the name temporal key. It is used to protect integrity, hence integrity protocol. So in TKIP, because that key is temporal, it is called as temporal key. Integrity protocol is because it uses a protection against integrity. So steps used for WPA. First is generating the seed. So here for generating the seed, the algorithm uses temporal encryption key, transmit address, and TSE. So TSE is a 48-bit counter. It is initialized to 1 every time the TKeep temporal key is initialized or refreshed. Each MPDU must be sent with a unique or different TSE to protect against replay attacks. It is incremented by 1 for each subsequent use. In the diagram, TSE is shown as IV plus EIV. Just remember that it is initialized to 1 and incremented by 1 for each subsequent use. So TSE is initialized to 1 and incremented by 1 for each subsequent use. So as per the diagram shown here, the temporal encryption key, transmit address, and TKeep sequence counter TSE are mixed by key mixer to generate the seed. Remember in WEP, only WEP key and IV were used to generate the seed. So here temporal encryption key, transmit address, and TSE are used for generating the seed. So similar to the WEP, the seed is fed to RC4 cipher for encryption, which will output key stream. So as you can see here, RC4 cipher algorithm uses this WEP key, which will generate the key stream. So on the other side, a Michael algorithm is applied on MSDU. So MSDU is nothing but the data and the mic key. So the Michael algorithm is applied on MSDU and mic key to obtain MSDU plus MIC fragment. This MSDU plus MIC after fragmentation will be MPDU. On MPDU, CRC32 checksum is applied to get the ICV, integrity check value, as shown here. So next XR is applied on the key stream and MPDU plus ICV to get the final packet to transmit. So in the final packet, we have the cipher text, which is XOR algorithm of NPDU ICV and key stream. We have EIV, we have KID, we have IV, and we have MAC header. So this is the combined flow. This is the combined flow. So initially, a key mixing is done using temporal encryption key, transmit address, and TSE to get the WEP seed. The WEP seed is fed to RC4 cipher. So output of RC4 cipher is key stream. So this key stream is XORed with MPDU plus ICV to get the cipher text. So the EIV is also added to cipher text along with KID, IV, and MAC address to obtain the final packet.